Good morning, dear students. Welcome to another session of Introduction to Data Structures and Algorithms. So in previous session, we started a discussion with respect to graphs, in which we saw what a graph consists of and what are its few of the applications. Henceforth, we'll again require these terms. That is, we'll be referring to vertices and edges. So when we have two representations, so these are the vertices, or sometimes they are also called as nodes, and the connecting element between these two is termed as a edge, or sometimes it is called as a link. So this terminology is required because we'll be using those things in variably. So we had discussed regarding what is meant by undirected graph and directed graph, and based on that, a few of the graph terminologies we had discussed. Then in the last session, right, we had discussed regarding adjacency matrix and path matrix. That is how we implement graph using these two methods. So how is path matrix different from the adjacency matrix? So that is what we had discussed. Last, what we have to discuss is regarding the adjacency list, how we implement graph using adjacency list. So again, we require for adjacency list, right? We require the adjacency matrix, and from that we develop the adjacency list. So before going into that, let us have a recap of what is actually adjacency matrix and how it is developed. Now, when we have a graph G, which is actually a set of combination related to the vertex or the node along with its edges or the links. So here we can see that. So since this is a directed graph, if I consider any node, if there is a directed link between the other nodes, say for example, 1 to 2, there is a directed link. So in that case, the adjacency matrix, which is represented by A, will be having a 1 which is allocated in that. That is, a 1 is assigned. 1 indicates that is a entry in the matrix is 1 if there is a directed path present between those two vertices or the nodes, and if there is no directed say path, there is no directed edge between the nodes, then the entry will be 0. So for example, 1 to 1 there is a directed edge, so therefore the entry is 1. 1 to 2 there is a directed edge, therefore the entry is 1 here. And 1 to 3, if you just see, there is no directed entry from 1 to 3, therefore this is 0. In the similar way, this entire table is being developed, and this is termed as the adjacency matrix. So a slight improvement of this one was the path matrix. So in this case, so just to have a brush up of those concepts. So here in this one, if you just observe 1 to 3, I'm not able to reach directly. But is there a path wherein I can reach node 3 in an indirect way? If you just observe 1 to 2, and from 2 to 3, I can reach. So in that case, if this is possible, then this is updated with 1. So that is Warshall's method, what we had discussed. So slight variation of those. So actual path matrix, what is done is you estimate this equation. You estimate this. So it will be the multiplication. If it will be multiplication and addition of the matrix what we have obtained. So we take A, which is the matrix. We take A raised to 2, which is square of the same matrix, and say cube of this matrix, and so on up to an. So this is what we do, and we end up with another matrix which will be similar size of which of adjacency list. Say if A is 5 by 5, the final matrix also will be a 5 by 5 matrix. So here we get entries. So if these entries are non-zero, we replace it with 1, indicating that there is a path present between those two nodes. So that is what will be happening. So in this case, when I use this, what happens is 1 to 3. I'll be able to reach, this will be a non-zero value, and this I'll be replacing with 1. Whereas the other values, if there is no path, it will not be replaced. It will be 0. So that is what is done. So instead of going with that method, a slight variation is introduced. So what is done is they make use of this equation, that is this logical parameter, which is Warshall's method. So this is your path matrix method. Slight variation of this one is gives you the Warshall's method, in which what you do is So you have estimated and you have replaced the non-zero values with 1, and zero values you have kept as it is. But in this case, what you're doing is, since if you just observe, there are multiple calculations involved, which are matrix calculations. So just to avoid those steps, what is done is, for example, from 1 to 1, I have a path. So path is present. From 1 to 2, there is a directed edge. So I can have a 1 over here. But what about 1 to 3? 1 to 3 directly I'll not be able to reach. So what is being given, what is being identified, whether there is a direct path present between these two or not. So if there is no direct path, whether there is an indirect way of reaching that node. So that is what is being looked out. So that is what is done in the Warshall's method. That is the updating the path matrix. So if I use this, so that is what this specifies. So P of ij implies that whether there is a direct path. So we had say 1 to 3, whether there is a direct path, or else is there any other indirect path. That is one, that is first I reach 1 to 2 and then 1 to 3. So that is what this is specifying. So this is like 1 to 3, if there is a direct path, use this, or if you have 1 to 2 and 2 to 3, if that is possible, you use that. So that is how you are building the path matrix using the Warshall's method. So that is what we had discussed in the previous sessions. So in this case, what you're doing is, if you just observe the implementation of the Warshall's method, in which we are building the path matrix, what we are doing is, so from here to here, if you just observe, it is nothing but you are developing the adjacency matrix. You are developing the adjacency matrix, which we termed as A. That is what is being done over here. And you're just printing what are those values. That is the adjacency matrix values. So this is what you're printing. So you have developed the adjacency matrix. Once you have developed the adjacency matrix, what you are doing is, initially you are updating the path matrix with this adjacency matrix itself. So what does this indicate? It indicates, see, that if it is 1, so I'll refer to this figure. So it is this diagram only which is being referred in that program. So what you have done in adjacency matrix, you get to know that whether there is direct path or not. So 1 to 1, there is a direct path. 1 to 2, there is a direct path. 1 to 3, there is no direct path. So this 0 indicates that. So 1 to 4, there is a direct path, and so on for all the nodes. So that is what is being done over here. So first, initial path matrix, you are updating the entire path matrix with the direct path values. Direct path values. Now what happens is, these zeros which are there, right? You need to adjust those. If there is a indirect path available, you will be updating with those values. So that is what you are doing here. So first you are updating all the direct paths which are available, which is nothing but the adjacency matrix gives that information. It gives you the direct path, that is 1 to 2, whether there is a direct path, 1 to 3, whether there is a direct path. If no, then it is being replaced with 0. So that is what is being specified over here. Now what you're checking is whether I can reach the other node in an indirect way. That is, I go to other node, and from that node, whether I can reach the other node. That is what you are, that is immediate neighbor, you are checking with those aspects. So that is what you are doing over here. So best example is node 3, direct I cannot reach. So therefore the entry will be 0 in the adjacency matrix. But if you just see 1 to 2 and 2 to 3, it is possible. That is what you are checking. So this is the logical implementation, what you will be looking out for. So in path matrix, what we'll be checking, whether 1 to 3, there is a direct path. So if I look at the entry, this is 0, or you are checking the logical parameter, or whether I can go from 1 to 2 and I can go from 2 to 3. So if you just observe 1 to 3, there is a path. So in path matrix, the entry will be 1. Entry is 1. And from say 2 to 3, is it possible to reach? So 2 and 3, if you just observe, yes, it is 1. So here what it turns out, it is 1 and 1, which is logical again 1. So 0 or 1 will be equal to logical 1. So that is, it is true. It is true. So if I write it in Boolean form, right, this is false because there is no path between those two nodes, and this is true, and even this is true in this case. So since both are true, what happens is overall, since it is an AND operation, since it is a AND logical operation, the overall result of this operation will be true. So now your ORing false ORed with true will give you a result of true. So what it is telling that indirectly you can reach node 3. So that is the information what is being updated. So that is what you are doing over here. So you can observe what they have specified. So in this equation, so which is actually the Warshall's method, that is the equation what you have used. So here, in order to implement these, what you are doing is you are implementing, say, if possible, you can go ahead with the logical operations. But since we are storing integer values, right? Since we are storing integer values, we cannot directly use the logical operations. You cannot use those. So what you have to do is you have to implement those logical operations. So as a functions. So that is what is being done over here. So in this and or operations you're performing. So overall, first what you are checking is you are checking whether you are first passing this AND parameter. You can just see a function within function you are performing. So here you can see that these two are ORed. So it is like 1, 3, the path is being checked, and it is ANDed. It is ANDed with 1, 2 and 2, 3. This is being checked over here. And next, this result has to be ORed with what? Whether there is a direct path or not. So based on that, the update will be happening, whether the path matrix entry has to be 1 or not. So that is what you are performing in this using this equation. So you're calling the OR function and you're calling the AND function. So that is what you're doing in this case. So once that is being updated, you can print and see what is the updated path matrix. So here, if you just observe, there is some change. What you can see between, there is some change between the adjacency matrix and the path matrix. So here you can see that 1 to 1 there was a direct path. 1 to 2, that is node 1 to node 2, there was a direct path. But in adjacency matrix, we can see that there was no direct path. But when you implemented the path matrix using the Warshall's method, what you can observe that indirectly I can reach this. So therefore, this entry is 1. So similarly, the other entries are also being updated. It is not that it is only checked with 1 to 2. Suppose if 1 to 2 there was no path, so it will perform with, say it will start with 1 to 1, whether it is possible, 1 to 2, 1 to 3, 1 to 4, and 1 to 5. And from that, whether you'll be able to reach node 3. So there will be one intermediate node, and that intermediate node, say I want to update 1 to 3 path. So first I'll check with, say 1 to 1 and 1 to 3 whether it is possible. Then 1 to 2 and 2 to 3 whether it is possible. 1 to 3 and 3 to 3 itself is possible. That is how the logical implementation is done here. Then 1 to 4 and 4 to 3 and 1 to 5 and 5 to 3. So you cross verify with all these. It is not only the node to what I am telling. So you'll be checking with all those parameters. And if you want to reduce the number of steps, right, you can make some logical estimates that 1 to 1, whether there is a path, and 1 to 3. If 1 to 3, naturally, if it is not there, then 1 to 1 and 1 to 3 will also be not be there. So this operations you can negate by making some slight logical changes in the program. So this is what you are doing in with respect to the Warshall's method. So now let us move ahead with the adjacency list. That is implementation of the graphs with the help of adjacency list. Now in previous two cases, what we saw that there is an adjacency matrix which is giving you the information pertaining to what, whether there is a direct path present between the nodes or not. And the slight variation of this gave me the path matrix using, say, the Warshall's method, whether indirectly I'll be able to reach the other node. That is, in this case, it is indicating that there is no direct path, but indirectly, can I reach this node? So that is what you're checking out. Now, in adjacency list, what is done is you make use of the linked implementations. You make use of the linked implementations. So in this thing, what happens is the graph is basically represented with a linked list implementation, which again makes use of the adjacency list what we have discussed. So that is the adjacency matrix what we have discussed. Now, in this case, what happens is, so here we can see that I have node one. I have node one. Node one will be having a list which will include who are the neighboring nodes present with respect to that node. Say, for example, if I just specify. So in this case, what is done is I have node one. Who are the this node one will contain a linked list. Will contain a linked list. What does this linked list contain of? It will be containing the information regarding the neighbors, of the node. So in this case, what happens is, if you just observe who all are the neighbors of this node, the one itself is the neighbor of this node because there is a path present. Then one is having 2 also, then one is having 4 also. 3 and 5 are not the neighbors. So in indirect sense, what it specifies is, it specifies who are the successors of 1. Who are the successors of 1. So if I start from 1, the successor of 1 can be 4, it can be 3, it can be 1 itself. So that is a linked list related to the neighbors is present in the adjacency list. So similarly, it will be applicable even for all the other nodes. So that is what you are looking out in adjacency list. So this is the representation of the graph. So if you just observe for 1, what will be the linked list associated with the neighbors of 1? It will be all these elements. It will be all these elements. That is, node 1 is the neighbor, node 2 is the neighbor, node 4 is the neighbor. So this is actually a linked list of the neighbors which are associated with node 1. And if there are no neighbors, then a null will be updated. A null will be updated in this case. Now, if I check for 2, who is the neighbor? So if since it is a directed graph, the neighbor associated with 2 is only 3. With 2 is only 3. So with 4, with 1, I am not having any directed path. With 5 also, I am not having any directed path. So therefore, the neighboring, that is a linked list associated with the neighbors of node 2, that is containing the information regarding the neighbors, will have node 3. And after node 3, there are no other neighbors which are present. So therefore, this will be updated with a null. So 2 is having only 1 neighbor, but 1 is having 3 neighbors. That is, 1 is including itself, and the other 2 are 2 and 4. So similarly, all others are being updated in the same fashion. Now, when we come to the last one, that is in as per the diagram what we observe. So if I just observe 5, are there any neighbors associated with this? So if you just consider this as the directed graph, you can see that there is no directed path between 5 to 3, 5 to 2, 5 to 4, or 5 to 1. So therefore, there are no neighbors. So directly it will be a null which will be updated in the linked list, which is associated with the list of neighbors for the node which is under consideration. So therefore, this is null. So here adjacency list basically contains a linked list information which has the information pertaining to the neighbors associated with the node which is under consideration. So in another point, it gives us the information of who all is the successor for the present node which is under consideration. So that is what they specify over here. So this is the adjacency list, what they have given. So now based on the concept, right? Based on this concept, what we have is we can look out at the logical implementation using the C program of the adjacency list. Now, since we have to store the information pertaining to who is the neighbor, whether there is an edge present. So this is telling that there is a directed edge present between 1 and 2. This is telling that there is a directed edge present between 1 and 1. 1 and 2, and 1 and 4. So this is the information what we have. Now what we have to do is we have to store this information in the form of a node, in the form of a structure. So here what we are doing is this vertex or the node what we are speaking. So we define information pertaining to these aspects, and what we require is we require certain information pertaining to the edges. So you can see that this is a pointer. This is a pointer which is pointing to its similar data type, that is struct vertex what we have declared. And it is you are specified that it will be a array of pointers, and it can store up to 10 pointer informations. 10 pointer information. So for example, here what they have done is they have declared it, and they have say declared a variable named node for this. And there are 10 nodes, that is in this case what they have specified is they have declared an array of 10 nodes which are of the type struct vertex, and each node will be each node in this array. Each node in this array will be having a edge and an ID associated with this. So now in our program, what we have to do is we have to update this information. We have to update, say if I start with node 1, whether node 1 to node 1 there is an edge or not. If yes, then I should update this edge information with respect to that node. So why again there are 10 elements which are declared for this pointer. So it might happen that if you're implementing the mesh network, if you just observe, I'm just taking an example. So if I have 10 nodes, right? If I have say, for example, I'll consider say 10 nodes. So I have 2, 3, and so on up to 10 nodes. It might be possible that this one node might have a directed path to all these 10 nodes. So that information has to be updated for each of the node. So for one node 1, whether there is an edge present for 1, 2, 3, so on up to 10. So if there is an edge, you update it with some information giving that there is a node present with this. Say I'll be writing it as 1. Then if 1 to 2 there is an edge present, you write it as 1. 1 to 3 there is an edge present, you write it as 1. If 1 to 10 there is no edge, you write it as 0. So in this case, what they are doing is they are updating with the address of that node element. So if 1 to 1 there is an edge, what is done is address of this information is updated in this edge field. Since this is an address, right? So you'll be writing the address of 1. If 1 to 2 there is a edge present, that is there is a link between these two, then you update the address of this node 2 in this field. So in this way, you keep on updating. Otherwise, what you're doing is you are updating the information with null. So for example, if 10, there is a no link, that is 1 to 10, there is no link. What you're doing is you are updating with null at that location. So this is giving you the edge information and whether there are edges present or not. So that is the implementation what you are looking out over here. That's the reason why you have declared it the pointer as an array of pointers. And all the pointers will be of the type struct vertex. That is, they'll be pointing to that data type. So that is what is being specified over here. So after that, you declare all the variables which are required, and then you take the information. So in this one, what you're doing is you are asking the user to enter how many vertices or nodes are present. So that information is taken. So if there are 5 nodes, so you try to see, you try to check out 1, 2, so on up to 5. So here also, you try to update this entire list. So that is, you try to build this adjacency list. So since there are 5, so one with 1, 1 with 2, 1 with 3, 1 with 4, 1 with 5. So whether it will be a null or not, that is what you will be updating in this case. So that adjacency list you will be building over here. So you take the number of vertices or the nodes which are present. Then after that, what you're doing is you are assigning IDs to each of the vertices or the nodes. Now, since you are using arrays, right, the index will start with 0. So here we had referred this one as 1, right? So if you're implementing it using the array, this thing representation, then what happens is the index of this one will be 0, index of this one will be 1, 2, so on. Okay, so no need to get confused. So that is how it will be updated. So node of 0.id is updated with value 0. Then I is incremented. Node of 1 is equal to 1. So these are the IDs which are given, which will help us to identify which are the nodes. And then you are using flush std in. So this is one special kind of function. What happens is whenever you are writing some function onto the screen, now what happens is repeatedly same character might be taken into the account. If you're pressing space and or white spaces and giving all the details, right, it might so happen that that entry, say the first entry what you have done, that might be stored. So if you have to flush those, so you use this function. So now we'll be concentrating on the logical part. So here you are assigning IDs to each of the nodes. After this, what you are doing is you are asking the user, so again you are going through the for loop, and what you're doing is, so initially you have assigned the ID, and what you're performing over here is whether there is an edge present between the nodes. Say whether 1 to 1 there is an edge present, so user has to enter either yes or no. If it is yes, right, then you have to update that node I. So in our case, that say I'll refer to it as the first node to first node, since it is a for loop, right? First node to first node, there is an edge. So what I have to update it with? I have to update it with the address of the first node, So that is what is being done over here. Else, what I have to do, I have to update it with a null. So similarly, what I'll be doing is 1j will be incremented, whether there is an edge present between 1 and 2. If yes, then what you do is you update the address of node 2 over here. So that is what is being done. Or else you will be updating with null. So this will be done for all the nodes, say 1 to 1, 1 to 2, 1 to 3, so on up to 5. And this will continue from 5 to 1, 5 to 2, and 5 to 5. So all this will be done over here. So this procedure itself gives me the information pertaining to the adjacency list. So this is updating the adjacency list. So once that is done, you can call the display function and print the information pertaining to the edges. So that is what is being represented over here. So from node 1, with what are the edges? So this is giving you the adjacency list. 1 to 2 and 1 to 3, there are edges. Then node 2, 2 to 1 and 2 to 3, there are edges. And here he has taken only 3 nodes or 3 vertices. And third node 3 to 2 and 3 to 3. So this is what he has specified. So if I look at this one, 1 to 2 there is a edge, and 1 to 3 there is a edge. So that is what is being specified. 2 to 1 there is a directed edge. So that is what this information is giving, and 2 to 3 there is another directed edge. So then 3 to 2 already there, and 3 to 3 there is one directed edge. So there is a self loop over there. So this is the program in which you are updating the adjacency list. So now let us move ahead and discuss one of the important aspects which are related to using the graphs. So it is an application of the graph, which is shortest path algorithm. Now, if I have to just take an example, suppose you start off from your home and you want to go to college. So there might be n number of routes possible. So you might, so it might be any way possible. So there might be some other this thing. So here there might be different routes possible. Now, as per your this thing, what you will tell that I want to achieve a shortest path. So shortest path has some different implications in your networking concepts. So in networking concepts, what happens is shortest path deals with a few other parameters. It is not associated only with the distance. So sometimes what happens is you try to achieve the path which is shorter in terms of, say, the cost, or shorter in terms of the jumps. So in simple way, I'll just consider that If you want to go from home to college, what will be the, say, shortest path in terms of cost? Say if I go directly, say it is costing me 10. It is costing me 10. Now, if I go from H to 1 and 1 to 2 and 2 to 4, so H to 1 will cost me 1, 1 to 2 might cost me 2, and 2 to 3 might cost me 3. So if I consider the total, what will be 1 plus 2 plus 3? So it will be 6. So this path is giving me a total of 6, which is less than this. So in terms of cost, if I just specify, right, this is the shortest path what is available. So it is just a implication what we can have depending on what cost parameter you are considering or what weight parameter you are considering. So based on that, we'll be defining the shortest path. If you are if you are using the number of jumps, say if you're using number of jumps, that is how many nodes you traverse. You want to reduce that. So for that purpose, you can go directly because just with the one single hop, right, you will be reaching the destination. But in this case, one hop, two hop, and three hop. So this is a longer path in terms of the number of hops. But this path will be the shorter one in terms of the number of hops. So this is just an example pertaining to shortest path. So in this case, what we are doing is we are considering these weight parameters. So these weight parameters. Till now, we hadn't specified these things. So we had just specified that there is a directed path between the nodes. Now, what is done is, what is the cost of moving from node 1 to node 2? So it is equal to 3. Cost of moving from node 1 to node 1, it is 8. Cost of moving from node 1 to node 3, direct path I don't have. So generally what is done is, this is identified as infinity. If there is a no path, then we identify initially it as infinity. So directly here you can see that it is infinity. 1 to 4, the cost is 4. So on, others are updated. So here, what does Wij imply? It implies the weight which is associated with the edge in moving from, say, node Vi to Vj. That is from 1 to 2 when you're moving. 3 is the weight which is associated with this edge. That is, if you're using this edge, with this edge, the weight is associated, or weight associated is 3. We sometimes call it as cost also. We sometimes term it as cost. 0 indicates that there is no direct edge between the corresponding nodes. That is 1 to 3, if I just specify, from 1 to 3, I am not having a directed edge. So that is what is being given over here. 1 to 1, there is a weight which is associated with 8. 1 to 2, it is 3. 1 to 3, there is no direct path. Therefore, it is updated with 3, sorry, a 0 over here, indicating that there is no direct edge between these two. That is from 1 to 3. Now, SP is the term what we'll be using. That is, this is the weight matrix. This is the weight matrix, and this is the path matrix. So shortest path matrix, shortest path matrix. So it is like the updated version of the path matrix what we have discussed. So SP will be identifying the shortest path matrix, which gives us information relating to the shortest possible paths between the nodes. So that information will be updated over here. So now, so that is in next slide, we'll be discussing regarding this. So so this is actually the initial step of the shortest path. What is represented is actually initial step. But what does SP give you once it is updated, right? It gives us the information pertaining to what is the minimum or the shortest path from in order to go from node 1 to node 1. Node 1 to node 3, what is the shortest? What is the shortest path? Node 1 to node 3, what is the shortest path? And so on until all the nodes are being done. Okay. So here, this is the weight matrix. This is the weight matrix. So previously what we are doing, if there was a path, we were updating it with the 1. That is the path matrix or the adjacency list, what we are doing, right? We are updating it with 1. Now, instead of 1, we update it with the cost information or the weight information, which is associated for that edge. So that is what you're doing in the weight matrix. So this is the weight matrix W, and SP is the shortest path matrix, which gives you the information pertaining to, once it is updated, it gives you the information pertaining to What is the shortest path in reaching in possible between two nodes which are present in the graph. So now in this one, right, just the slight modification of Warshall's method we need to apply. So that is what from 1 to 1, there is a direct path. So you have updated. So previously you just updated it with 1. Now you're updating it with this information. Now here 1 to 2, the cost is 3, and 1 to 3, if you just observe, there is no direct path. But in Warshall's method, what you did, you observe that 1 to 2 and 2 to 3 you are able to reach. So therefore you updated it with 1. But what is done is, instead of 1, we need to update this one with respect to what is the cost of moving from 1 to 2 and 2 to 3. That is what we have to update over here, which gives you information pertaining to the shortest path. So how do we start off with obtaining the shortest path matrix? So initially what you do is, first you build the weight matrix. First you will build the weight matrix. So if you just observe, so what is the cost, or what is the cost of moving, or what is the weight of moving from 1 to 1? So I have to use this edge. There is a directed edge. So 1 to 1, the cost is 8. That is being updated. 1 to 2, the cost is 3. That is being updated. 1 to 3, there is no directed edge between this. That's why it is updated with 0. 1 to 4, the cost is 4. And 1 to 5, if you just observe, there is no directed path between these two. Therefore, it is updated with 0. So similarly, what you do is, with respect to all other nodes, you update this parameter. Say, I'll just take example of 5. So 5 to 1, can I reach? Is there a directed path? No. So therefore, this is updated with 0. 5 to 2 also it will be 0. 5 to 3 also 0. And 5 to 4, if you just observe, I'll be able to reach. But what is the cost associated with this, or the weight associated with this? It is 1. So you update the weight information pertaining to moving from each of the nodes. So here you are considering the directed nodes. So 1, 2 directly whether I can reach 2, 1 directly whether I can reach 3. So that is what you are updating in the weight matrix. So once you obtain this weight matrix, right, what you do is you update the initial part of the, say, the shortest path matrix. So this is the initial update. So before going into actual updation of the shortest path matrix, right, initially what you have to do is, from this weight matrix, you obtain this initial, say, shortest path matrix. So in this one, what is done is, what you do is, you consider 1 to 1. So the same value you update over here. 1 to 3, the same value update over here. But what if there is no path, direct path between present between the nodes, right? You update it with the value which is identified as infinity. So you replace that. If there is no direct path between these two, you update it with the value of infinity. So it indicates that you will not be able to reach from 1 to 3 directly. That is what this information is given. So all these 0 values which are there, it gives an indication that there is no direct path between them. So therefore, that is being updated with infinity over there. And remaining all right, you are updating with its respective cost value of reaching directly. So that is what you are doing. So only change is all the zeros in the weight matrix are replaced with infinity, giving an indication that directly I cannot reach that node in the path matrix. So this is the initial update. So once this is done, right, what I have to do is I have to check whether I'll be able to reach, say, any of the node, say from 1 to 1, whether I'll be able to reach this node in a still lower cost than this. So whether I'll be able to reach still with a lesser cost. So that is what I have to check out, whether I'll be able to reach 1 to 3 with a cost which is lesser than this, whether I'll be able to reach 1 to 3 with a cost which is less than this value, that is infinity. So that is what we have to check out for. So for that purpose, you are updating this with infinity. If it was 0, right, then you would not be able to implement the shortest path, because 1 to 3 indicate, if it is 0, then the cost of reaching node 3 would be very less. So that is what you are specifying in the shortest path matrix. So that is what you are doing. So if you just start with the node 1, If you start with node 1, 1 to 1, the cost is 8. 1 to 1, the cost is 8. So 1 to 2 and 2 to 1, can I reach with a lesser cost? No, I cannot reach that. So 1 to 3, 1 to 2, 1 to 2, the cost of moving from 1 to 2, or the weight of moving from 1 to 2 is 3. Is there any alternate way? Say I'll try with 1 to 2 and 2 to 1. That is the first this thing what I tried. Then 1 to 3 and 3 to 1, 1 to 4 and 4 to 1, and 1 to 5 and 5 to 1. So I need to check for all the values. So if not possible, then I move ahead. So this is the final value what I'll be obtaining. So next what I'll be doing is I'll be moving to the next node. From 2 to 1, can I reach? No. From 2 to 1. So if I just check with this, 2 to 1, if you just check out, I'll not be able to reach directly. Whether there is any indirect path. So if you just see from 2 to 3 and 3 to 4, I'll be able to reach. So what is the cost of this? The cost of this is 11. So in this way, what I have to do is I have to check for all the nodes and whether I'll be able to reach all the other nodes with the help of its neighboring nodes. So that is what I have to check out for. So here you can see, if I consider this one, from 2 to 1, can I reach directly? No, the cost is infinity. That is what is present over here. Can I say 2 to 2 and then 2 to 1? Still not possible. 2 to 3 and 3 to 1, is it possible? 2 to 3 is what? 2 to 3 is 7 and 3 to 1 is what? 4. So if I add this total, how much it will be? It will be 7 plus 4, which is equal to 11. It will be equal to 11. So if you just observe, 11 is less than the infinity value. So what is this telling? That I can move from node 1 to node 2. I can move from node 1 to node 2 with the cost of 11. But in order to do that, what you have to do is you have to first move to node 3 and then you have to move to node 1. So this is nothing but the Warshall's method what we are specifying. If there is no direct path, check out with the indirect path. Check out with the indirect path. Now in shortest path, what we are doing, we are updating that indirect path with its cost value. We are trying to reduce the cost. That is what we are doing here. So infinite. So instead of that, I have to update it with 11. So here you can see that what is the cost of moving from 2 to 2? It is infinite. It is infinite. Can I move from 2 to 1 and then 1 to 2? No, because I don't have a direct path between this. I have this path, but what happens is that I cannot be updating over here. So here what we do is, so we need to check all the alternate ways, So if you just identify, so what was the previous update with the 2 to 1? It was 11. It was 11. So this is the updated matrix which will be utilized when we move to node 2. So from 2 to 1 directly I cannot reach, but I can move to 3 and 3 to 1 in the cost of 11, with the cost of 11. And from 1 to 2, there is a cost which is associated, which is 3, So if you just see what happens is 2 to 1, I have to first move to 2 to 1 and 1 to 2. 1 to 2. What is the cost of moving from 2 to 1? It is 11. What is the cost of moving from 1 to 2? It is 3. What is the total cost? It is 14. So that will be updated over here. So this is how the implementation goes around. So since this is a directed graph, right? That is digraph. It's a directed graph. This kind of update will be there. But if it was indirect graph, right, what would happen is, that is non-directed graph, right? What would happen is cost of moving from 1 to 2 is 3 and 1 to 2 is 3 and 2 to 1 is also 3. But since it is directed, right, this change will be occurring over here. So here it will be 11. So using this new value, you'll be able to reach itself with a cost of 14. So in this way, what you do is you try to update the entire shortest path matrix. So that is what you are doing over here. So this is what you are considering. Now what happens is you can see that slight variation you have to just check out. That is, you need to consider the minimum value which is associated with the path. Whether moving from one to one directly costs me less, or whether moving from one through the other path costs me less, whether this is lesser or this is lesser. So for example, here we considered, so moving from 2 to 1 actually costed me 11. So directly if I did, it costed me 11. But if I moved from 2 to 3 and 3 to 4, 3 to 1. So that is 2 to 3. And from this node, I tried to reach the node 1. So what was the cost? The cost was 7 plus 4, which was 11. So that is being updated over here. So out of direct path value is infinity, and indirect path value is 11. Which one is minimum? Minimum is 11. That is what you are updating. Whether direct path is less or indirect path is less. So that value you are updating in this case. So this you need to apply for all the nodes and all the combinations. So once you do that, you will be obtaining this updated shortest path matrix. So the Warshall's method, what we discussed previously, right? So that is what is being done. So there, what you did, you just checked whether it is 1 or 0. Now here, what you're doing is the same implementation. You are using the path matrix value. You are using the, what is the weight associated with that. You are considering that and updating the value. Only that's the change what you can observe over here. What is the shortest path value? There in previous Warshall's method, what you are doing, so here you can see that you are updating it with 1 or 0 value, with 1 or 0 value. But now what you're doing is, instead of, if it is 1, what is the cost? If it is 0, it will be infinity. It will be infinity. You are trying to update this value over here. So that is what you are trying to implement. So this is the shortest path algorithm, what we implement using the Warshall's method. So, and the same this thing, if you just observe, what you're doing is, first you are updating the path matrix, which actually contains the weight, which is nothing but, first you can update the adjacency. It is also indirectly giving you the adjacency matrix also. It is giving you the adjacency matrix, but instead of updating it with 1 or 0, you're updating it with the weight values, which gives you the path matrix. So that path matrix you're just printing over here, and what you're doing is, here you can see that initially all the entries in the shortest path are updated with what, 999. So since in systems, in computers, right, we cannot have infinite representation. What we do is we consider one value. Say in this case, 999 is considered as infinite value. So that is what you are specifying over here. So that is what is being done. And after this, what you're doing is, shortest path is initially updated with this path matrix value itself. And then you apply the Warshall's method. So in Warshall's method, what you're doing, you are trying to see whether the direct path gives you less or whether the indirect path gives you less. That is what you're trying to check out. That is the implementation. So this is nothing but a different way of representing the Warshall's method. So once that is done, you'll be obtaining the shortest path matrix, which is the updated parameter over here. So this is all for today. Let us meet in the next session. Thank you.